Let's assume we want to analyze the energy in an open channel. Because it is open to the atmosphere, we can say that there is no pressure head. Also, for the sake of simplicity, we will define the energy at any given point in the channel as relative to the bed slope, and this will eliminate the need to account for the elevation of the channel as part of the potential energy. In this situation, the only way to define the potential energy of the channel is to measure the flow depth. Assuming that the shape of the channel as well as the flow rate conveyed in the channel both remain constant, the increase in flow depth also increases the potential energy, 1-to-1. If we decrease the flow depth in the channel, again with the flow rate and the geometry remaining constant, we force the flow into a smaller area. As we decrease the area, we must compensate by increasing the flow velocity, which increases the velocity head in the channel. Alternatively, as we bring the flow depth up, the area enlarges, and with the Q staying the same, we see a decrease in the velocity. Because the velocity is defined with a v squared term, the shape of this relationship is parabolic, as seen here. The summation of the potential and kinetic head in an open channel gives us what is called the specific energy profile. If you enjoyed your first term of calculus, you may look at the specific energy curve and ask, I wonder where the minimum point is along that curve, which is why I'm showing it here as y sub c. Taking the derivative of the energy with respect to the flow depth gives us this relationship. The dA dy term is actually another way of expressing the top width of the flow in the channel. With a little algebra, we can define an expression to help us calculate the critical depth, or the depth at which the specific energy is minimized. Unfortunately, both the area and the top width expressions are in terms of the critical depth, and they cannot be separated out. So the solution to the critical depth is found iteratively. However, in the case of the rectangular channel, the base width of the channel is the top width. So we can do a little substitution and a little simplification to obtain the following expression, which will allow us to calculate the critical depth directly, simply knowing the discharge flow rate and the base width. Again, this case applies only for rectangular channels. Going back to the general case, if we look at the expression of q squared t divided by ga cubed, we get a dimensionless number, and if we take the square root of this expression, we define what is known as the Froude number. In an open channel, we define the Froude number as velocity divided by the square root of gd, where d is known as the hydraulic depth of an open channel. The hydraulic depth is defined as the flow area divided by the flow top width. When the Froude number is equal to 1, then we can state that the flow in the channel is critical. When it is less than 1, then we state that it is subcritical. When it is greater than 1, we state that it is supercritical. I think you're getting the point here. Visually speaking, when a flow rate is classified as supercritical, this corresponds to a higher velocity, which also means that the flow area is small and the normal depth would be lower than the critical depth. Alternatively, when the normal depth is greater than the critical depth, the flow area can be classified as subcritical flow because along with the deeper normal depth comes a greater flow area and a slower velocity in the channel, hence the smaller Froude number. Why on earth do we care about all of this? As it turns out, we can engineer systems that handle supercritical flow as well as subcritical flow without any problem. The problem arises when we have a channel that for whatever reason transitions from supercritical to subcritical flow. This transition is a type of rapidly varied flow and is known as a hydraulic jump. When we design channels, we pick the channel shape and the bed slope of the channel. We want to design our channels so that they are solidly supercritical or subcritical, but not in between, because When it is in between, the flow rate is not stable. Therefore, we must also calculate the critical slope of our channel to ensure that the slope we have chosen does not come too close to the critical slope of the open channel. To calculate the critical slope, we solve Manning's equations for the friction slope. Inside the A and R terms, we insert the critical depth, or y sub c value, to calculate the critical area and hydraulic radius. All of these tools, meaning comparing normal depth to critical depth, calculating the Froude number, and calculating the critical slope, are methods of assessing whether or not our channel is going to remain within the flow regime we expected when we sized the channel. As a result, some agencies specify criteria for one or more of these checks to make sure that we do not design a channel with an unstable flow.